Today we'll be learning chemical kinetics and understanding what this concept is all about. Welcome to Introductory Chemistry. I am Mihir here. Imagine you're watching a busy train station, people moving in and out, continuously colliding with each other. But imagine with each and every collision, with each and every person colliding with each other, something happens. Maybe people's wallets swap, maybe their tickets get exchanged, maybe there's a new travel group that forms every single time a collision happens. This is practically the idea of a reaction that occurs in chemistry. Molecules collide, things change. But here's something that's really important to understand. Knowing a chemical reaction will not tell you how fast it's happening. That's why chemical kinetics is important. It studies the rate at which a reaction occurs. You get two major important questions answered. One being how fast is the reaction, and secondly, by which mechanism or pathway does it occur. Why is this important to know? Some reactions like bomb blasts, explosions happen in milliseconds, whereas some reactions like rusting take over years to happen. Understanding these rates helps us create and design industrial processes, preserve food, control pollution, and even help develop medicines with precise release times. Chemical kinetics and thermodynamics. These are both equally important in understanding what a chemical reaction is like, but they're drastically different. In what sense? Thermodynamics tells you if a reaction can occur or not. It tells you about the feasibility of the reaction, whereas chemical kinetics tells you about how fast or slow a reaction that is feasible will proceed. Now, where does this knowledge of chemical kinetics become important? Say, as an example, you're a pharmaceutical chemist and you have developed a new painkiller tablet. You want it to be dissolving in the body, in the stomach, within 15 minutes. So how do you ensure that? Maybe you'll take a bigger molecule, have it break down into your painkiller molecule within 15 minutes. That's where you use chemical kinetics. You will simulate, you will test out, and you will figure out which molecule, when started with, breaks down within 15 minutes to give you your target component. This is very simply what chemical kinetics is all about. This is what a scope is like. Now let us understand what the rate of a reaction really means. Imagine you're on a road trip. This is something I often do. I go from Mumbai to Pune quite often. You leave at 8 a.m., reach by 11 if you're very lucky. The distance is around 150 kilometers. What do you think the average speed is? Simply distance upon time. 150 kilometers by 3 hours, you're going at a good pace of 50 kilometers an hour. But if you check your speedometer at say exactly 9:15, you might see that the speed is maybe 70 kilometers per hour. That's your instantaneous speed. These things are something I've studied in kinematics already in grade 11. But why am I talking about this now in chemical kinetics? You will see similar concepts within chemical kinetics as well. The rate of a reaction calculated over a range of finite time can simply be represented as the change in the concentration of the product over time, or the negative of the change of reactants over time. Now, it is extremely important to understand why that negative sign exists. When you're looking at the change of product, you have your product increasing with time as your reaction proceeds. That's what we want to happen. So final concentration minus initial concentration will always be a positive value. Change in time is going to be positive value, thus the entire ratio is a positive value. Whereas your reactants are getting consumed in the reaction. Thus, your final reactant concentration will always be lesser than the initial value. Your difference becomes negative. Your ratio would have been negative if there was no negative sign that we added before the ratio. Now that we add that negative sign, that becomes positive. We have normalized the reaction and thus the ratio remains positive. The rate remains positive. If you do not put the negative sign, you will not get the right rate. What now? The instantaneous rate at one particular instant, in the terms of reactant, we look at it as minus d of the concentration of reactants upon dt. D by dt is giving you the instantaneous rate, whereas delta by delta t is giving you the average rate. Here's a homework for you people. Why do we use delta for a larger range of time, whereas we are using d for a small instance of time? You have been taught very normally that We use D for a very small change. Why so? I want you people to look that up and answer in the comments below. Now, whatever this rate of reaction is, change in reactant or change in product over time, can be plotted on a concentration versus time curve, which gives you an idea of how your reactant slash products change. The slope at any particular time will of course obviously give you the instantaneous rate. Say you're monitoring the decomposition of hydrogen peroxide in a lab. The reaction is slow, pretty slow at the beginning. It will speed up as bubbles start forming and then slows again once the reactants are used up. You take readings every 5 seconds and plot that on a graph. That is exactly where you notice that the slope change in multiple different points over time. That's how you know that the instantaneous rate at each of these points are different. You've quantified the slow, the speeding up, and the slowing down once again. Let me give you people a quick question for you to answer at home. If I have a very simple reaction of A which is becoming B, the concentration of A decreases from 0.8 to 0.4 in 40 seconds. What is the average rate of the reaction? And if the instantaneous rate at 20 seconds is 0.008 mole per liter second, explain the difference between this and the average rate. Answer this in the comments for me. And that's how you will know you have understood this concept very well. Before we proceed, this is a snippet of introductory chemistry for grade 12. We run similar programs for grades 9th, 10th, 11th, 12th in physics, chemistry, biology, and math. We're given signature personalized learning experiences for your learning challenges to be mitigated and for your learning goals to be achieved. What we do at Learners Club is we sit with you one-on-one to discuss exactly what you need to achieve within your learning journey. So if you are interested in knowing more about our programs and getting a free analysis of your current learning from me and from my expert mentors, you can click the link in the description for a free learning audit call. On there, you and I or my other mentors will guide you exactly what you need to do to ensure that your learning is top-notch. Again, the link is in the description down below, and you can check out our website for all of our other services. Now, moving back to our lesson. Think of baking cookies. If you double the amount of chocolate chips, it might not change how quickly the cookies bake. But if you raise the oven's temperature, they may bake faster or might even burn. In chemistry, the rate law tells us how the ingredients actually influence the speed at which the reaction occurs. Say if I have a reaction like this, small a capital A plus small b capital B gives you some products. The rate law is defined as some K multiplied by the concentration of A raised to some X multiplied by concentration of B raised to Y. What's important in this formula? Firstly, the K is something called the rate constant, which is fixed for any reaction that's occurring. And this rate constant only depends upon the temperature at which the reaction occurs. The X and the Y are reaction orders. What is extremely important to understand is these X and Y need not be equal to A and B respectively. Very important to understand. The only cases where it's equal to A and B is if A and B is if this reaction is a rate determining step, number one, and only if it is an elementary reaction will X be equal to A and Y be equal to B. Otherwise, these X and Y are usually determined experimentally. The order of a reaction is defined as X plus Y. So whenever I ask you what is the order of a reaction from the rate law that is given, you add up X and Y. The other important thing that you need to understand when you look at this rate law is something called as molecularity. Depending upon the number of distinct species present in the rate law, the reaction can be unimolecular when it's only one, bimolecular when it's only two, trimolecular, tetra, so on and so forth. Molecularity need not correspond to the order. We will see examples when we solve questions, but if you have a bimolecular reaction, it need not just be a second order reaction. It could be a third, it could be a fourth. And if you see a unimolecular reaction, it need not be always a first order reaction. It could also be a second or a third order reaction as well. So the rate law gives you a very clear picture of how the concentration of the reactants impact the rate. Apart from the concentration, temperature is a very important factor. If you remember my first example of the train station, as collisions occur, you have things happening. As molecules collide, a reaction proceeds. More molecules gave you more collisions. If I increase the temperature, the kinetic energy within each of these molecules increase, they vibrate even more rapidly, more collisions thus occur. If I have a catalyst, it requires lesser initial energy to proceed with the reaction. Now, before I even go into the catalyst concept, I want you people to understand what this concept of activation energy really is. For any reaction to proceed, it needs some amount of energy. Why? As I simply mentioned, the kinetic energy within these molecules is what drives it to collide with each other, what drives them to collide with each other, and for the reaction to proceed. If there is not enough energy within these molecules, they will not collide, the reaction will not proceed. So that minimum amount of energy that you need to provide to a reaction is called as an activation energy. Sometimes the environmental factors are enough for a reaction to proceed. Simply, if I mix an HCl and NaOH, you have the reaction proceeding at room temperature, whereas some reactions proceed at lower temperatures because at higher temperatures the molecules may degrade, or you need to heat the reaction for it to proceed. A catalyst reduces this activation energy barrier by changing the mechanism itself by which this reaction proceeds. So if I was going from A to B to C, my A to B step might involve another step where A is binding to my catalyst. Now this energy that is required for A to bind to my catalyst and my catalyst to bind to B as well, this is lower than from A to go to B. Thus, a catalyst is able to lower the amount of energy that I need to put in for this reaction to proceed. The nature of the reactant is also important. Ionic reactants usually perform better than covalent reactants, because of the energy that is required to form these bonds. And when you have solid reactants, the higher the surface area, the more molecules that are exposed, the faster the reaction occurs. Let's maybe think of an example. Say you're studying the reaction between nitrogen dioxide, NO2, and carbon monoxide, CO, which produces nitrogen monoxide and carbon dioxide. Experimental data shows that doubling the NO2 concentration quadruples the rate, but doubling CO has no effect. What will be the rate law? If you see that only NO2 is impacting the rate, and if you double, it's quadrupling. Thus, the rate law becomes rate is equal to K times NO2 square. Simply, if I increase NO2 by 2 times, rate is increasing by 2 raised to 2, 4 times. Here, the reaction is a second order unimolecular reaction. But with respect to CO, it's a zero order reaction. Another question that I would want you people to solve at home, if the reaction 2A plus B is giving me some products, has a rate law of K is equal to A square by B, A square times B. If the concentration of A is doubled and B is halved, by what factor does my rate change? Solve this and let me know the answer in the comments. Let's recap whatever we have done so far. We have looked at what chemical kinetics is. We have looked at what a rate of a reaction is. We looked at what a rate law is, and we looked at what factors determine the rate of the reaction. Imagine a bucket of popcorn that you have. If people grab at random but at constant rate, regardless of how much is left, that is like a zero order reaction. It does not matter to the people who are taking the popcorn as to how much is left, but they just keep on taking it. That's zero order. Keep that mental picture in mind. If, say, people are looking into how much popcorn is left, if the rate depends upon that, the more that people see that popcorn is left, they want to take it up faster. If they see that there is less popcorn, they might hesitate a little bit. And that's like a first order reaction. And if, say, people are taking popcorn only in pairs, the rate will slow down even more as the popcorn quantity decreases, because you're only taking 2 at a time. That's a second order reaction. So now if I want to rate the concentration of the reactants and the time that it takes for the reaction to occur, I can use whatever knowledge that we have gained till now to derive certain equations. So let's take a zero order reaction where the concentration really does not matter, and we are looking at A becoming B. I can express the rate as equal to being K or as minus dA by dt. Now if I equate both, I get minus dA by dt is equal to K. I take dt to one side, integrate it throughout, and I get this equation of A is equal to A naught minus KT. Rearrange it a little bit and compare it to y is equal to mx plus c. Do you see? If I plot a concentration time graph, The intercept gives me the original concentration, the initial concentration of my reactants, and the slope gives me the rate of the reaction. Now, if I want to calculate something called as the half-life, what does it mean? It means at the time at which my final concentration is half the initial concentration. So my A in my equation is now A naught by 2, and T becomes T half. I rearrange things, I get T half is equal to A naught by 2K. See, for a zero order reaction, the half-life depends on the initial concentration of the reactants. Very unique, because now when we compare it to the first order reaction, where dA minus dt is equal to Ka, your rate law, your rate depends upon the concentration. Rearranging things and integrating, I get ln of A is equal to ln of A naught minus Kt, or A is equal to A naught e to the power of Kt. This is an exponential graph, but if I say plot ln A versus T, we get a straight line, logical, and the slope there also is K. But now let's calculate the half-life. Ln A naught by 2 minus ln A naught is equal to minus Kt. Rearranging things, I get ln A minus ln A naught is equal to minus Kt, or ln A naught minus ln A is equal to Kt, or Kt half rather. A is equal to A naught by 2, so ln A naught minus ln A naught by 2 is equal to Kt. Using our knowledge of logarithms, we get as ln 2 is equal to Kt half. Ln 2 is 0.693, so you get a T half as 0.693 by K. For any first order reaction, your T half does not depend upon the concentration of your reactants. You can also calculate this for a second order reaction where minus dA by dt is equal to Ka square. Rearrange things, integrate things, you get 1 by A is equal to 1 by A naught plus Kt. When you plot 1 by A by versus T, you get a straight line, logical. Substitute A is equal to A naught by 2. Rearrange things, you get a T half as 1 by K A naught. Here, as your concentration decreases, your half-life increases. In zero order, your concentration increase, your half-life increase. So that is whatever you have understood till now about how the concentrations and time will relate. The questions for these half-life calculations and rate calculations are extremely important for any exam. So I will request you people to practice that for yourself with whatever knowledge I've given you for now. Another quick check question that I can give you people as of now itself is, if a zero order reaction is having the rate constant as 0.01 moles per liter per minute and initial concentration is of 0.5 moles per liter, find the concentration after 20 minutes and find the half-life. Calculate, comment, and you're good to go for the next section. Now say you want to know where you can apply this knowledge of chemical kinetics in this world that you're living in right now. Possibly in the next 5 years, where AI and AI powered robots may take over doing all of the dirty work, all of the hard work. What stays here for you? What's important? Your job becomes designing and creating things. Imagine you're creating a drug and you want to calculate how long they're effective. First order kinetics. Zero order kinetics in patches and pills ensures constant medication. Preservation, enzyme activity control, optimizing reaction conditions, petrochemicals, pollutant breakdowns, ozone depletion, ELISA, medical diagnosis, metabolic studies, automated data fitting, predictive modeling, process optimization, drug discovery. All of this is still possible in a world of AI and AI taking all of your jobs away. So don't underestimate whatever you're learning now. These were very quick applications that I could give you right now. With this, we will wrap up today's section for chemical kinetics. I have attached a PDF in the description for certain practice questions and solutions to certain questions in the same way as I've been discussing with you on this video right now. Solve them, get a hang of these questions, and with this, you'll be able to understand and complete chemical kinetics properly. So we looked at what chemical kinetics is, we looked at what a rate of a reaction is, we looked at how concentration impacts it, how time gets affected, how both of them are related, and we looked at certain applications. With this, we'll wrap up today's lesson. This was your snippet of introductory chemistry for grade 12. As I've mentioned previously, we run similar programs. If you're interested in getting your learning audited for free from me, the link is in the description. Check it out, schedule a call, and make the most of your learning. Of course, like, subscribe, share, anything to show that you really have understood and want more of this content. That gives me and all of my mentors motivation to do more like this for you people, for our learners. So please make sure to make the most of all of this. With this, I will see you in the next one. Thank you and happy learning. And make sure to learn more at Learners Club.